Hi, my name is Silas Joy, and I am doing my BSMS in Computer Science.
Hi, I'm Amanda Blanchard. I'm also doing my BSMS in Computer Science.
Hi, I'm Robin Husman. I'm doing a bachelor's in mathematical sciences and a bachelor's in computer science.
Hi, I'm Jaime Ortiz, and I'm doing a bachelor's in computer science.
Hey, I'm Nil Costelli, and I'm doing a bachelor's master's in computer science.
So to first dive into the motivation behind our project, media is a key way that people get information about various topics, including current events and real-world scenarios. However, a lot of information in the media is often very biased. So one study done about the Iraq War found that 40% of Fox News viewers falsely believe that the war was justified by weapons of mass destruction found in Iraq. So as we can see, based on different sources of media and how they're portraying information and the bias contained in it, it can really change the way people view a whole current event or a situation in general. So this picture kind of also gives a highlight of that, how when you're only showing a certain set of facts and there's different bias involved in what we're seeing, we often don't get the full picture and see the true facts behind something. So an important aspect of this project is detecting media bias, since that's the goal of our model. So two ways we looked into doing this is on context level, which is more about how information is framed in the overall situation. And also we looked into sentence level bias, which is more about how words are chosen and the specific language used. So in this image on the bottom here, this is focused on the sentence level wording used and how it changes how we perceive the topic. So on the left here, they're talking about a domestic terrorist attack. And on the right, they're talking about a mostly peaceful protest. So these two different languages can be used to describe the same topic, but give very different meaning. So understanding how to detect these differences and see both sides of the story to get a full picture and really understand the true meaning behind this and be able to understand where bias is coming from.
In order to evaluate bias in a statement, we use a language processing task known as sentiment analysis, which is the task of extracting subjective information from textual data. This task has been used to determine the emotions in a statement, to recognize whether a statement is positive or negative, or in our case, to identify whether political bias is present in a statement. In our case, we're using a binary classifier for this due to the limitations of our dataset, but a more advanced training set would allow for significantly more nuance in this task. Currently, deep language models and large language models are able to perform sentiment analysis with a pretty similar performance output, but we use a mix of both in our solution to demonstrate that. We've trained 4 separate models on our training dataset: BERT, T5, Roberta, and XLNet. And the outputs of that are considered by our final evaluation step for one final output. We used 2 different evaluation steps, majority rule voting and neural net evaluation, to compare their performance in our results.
Next, we're going to talk about related works of the state-of-the-art methods. So first, this article is an overview of media bias as a whole and how it has been used in artificial intelligence previously. So the big takeaways from this is different data sets that were available to use for AI media bias detection. So the chart here represents different data sets, the size, instance rating, annotation, year, and reference to them. So this gave us a great high-level overview of the topic as a whole. Currently, where different studies have focused and gave us references to look into more. Next, our first state-of-the-art method we decided to use was BERT. In this article, In Plain Sight, Media Bias Through the Lens of Factual Reporting, it dives more into fine-tuning BERT on media bias data, and they found evidence that information bias appears in news articles more frequently than lexical bias. And in this table below, it focuses on the metrics they derived from using BERT. So this shows us that BERT has been effectively used before in bias detection and would be effective for our methods as well.
Another model we employed was Roberta, which was established on BERT and then improved by more pre-training. We know Roberta can do this kind of work because of this example by the Bipartisan Press. They used Roberta, along with testing in multiple other models such as BERT, to try to create a model that could predict bias in entire news articles. They did this on the sliding scale of -42 to 42. This was based off of a pre-existing dataset which ranked articles based off of their left wing, -42, or right wing, +42, bias. They then took this model and ran it on a new dataset of different articles. Many of these were CNN and Breitbart articles, which is why their results show a largely slight left-wing emphasis.
ExoNet is a generalized autoaggressive pre-training for language understanding. As I said in other presentations, it captures bidirectional context. It doesn't use masking, use random permutations, maintains the relationship between the words. It's effective at handling the relationships between the words because it doesn't just mask and forget the word, maintains the context in the sentence, but also requires more resources. And this model is it's used in language translation, question answering, and text classification, as we're doing in our bias detection models. It's a really good model, and that's why we chose to use it.
T5, or Text-to-Text Transfer Transformer, is a large language model designed to explore the limits of using transfer learning for language processing tasks. T5 treats everything as a text-in, text-out problem using encoder-decoder transformer architecture, compared to something like BERT, which uses encoder-transformer, and it's designed to perform a wide variety of natural language processing tasks that many deep learning models are capable of performing individually, but not all at once.
Now, another system we've looked at is called BiPol. BiPol, named for bias and polarity, is a two-stage system designed to augment existing models with more detailed information about kind of the possible directions and topics of bias in the text. Now, in the first stage, which we call the corpus level analysis, BiPol relies on an existing model, probably one of the ones that we've discussed here. And it uses that model to rate a block of text as a whole as biased or not biased. And then if it's marked as biased, BiPol enters the sentence level analysis, where it will kind of take the segment of biased text and then it will count terms in it. It will measure the relative frequencies of various potentially sensitive terms. And the idea here is to give some insight into kind of in what way the text is biased. Is it about gender? Is it about sexuality? Is it about race? And kind of pictured here is one of the types of graphs it might spit out. BiPol, a couple strengths. It can easily have new axes of bias added by you add new lexica of sensitive terms. It's kind of interesting because it inherits a lot of its weaknesses from its base model. All it's doing is kind of adding information to that. It can't possibly make the base model more accurate. It all kind of does come back to that foundational corpus level analysis, that corpus level assessment. All it can do is kind of add some more detailed insight in the hopes of explaining its findings better. Now, next, Amanda's going to tell us about our kind of high-level proposed solution.
Next, we're going to dive into our proposed high-level solution of detecting media bias using artificial intelligence. So our first main decision we needed to make was what dataset to use when training our model. So we looked into 3 different datasets commonly used for media bias detection, such as BASIL, BABE, and MBIB. BASIL is done on the level of event spans, while BABE is done on sentence level, and MBIB is a combination of 22 datasets and contains different levels, different numbers of spans, and various different sources. The main differences to highlight here is that BASIL is done on news articles, so is BABE, and MBIB also contains social media. The main difference that made us decide to go with BABE for this was that it was annotated by experts, and due to media bias being a very subjective area, we decided we wanted to really prioritize having annotations done by experts to ensure our model was trained best.
This is the workflow diagram for the BERT model. It starts by tokenizing the sentences and then running multiple different pre-training tasks, which include next sentence prediction, where you give it a sentence and it tries to predict what will come after that, and masking and masked language modeling, where it will mask random words in a sentence and try to predict what those words should be. It has bidirectional context understanding, so it can look both directions in a sentence to see what word would fit the context, and they can be fine-tuned on a specific data set, such as one of the ones listed here.
For individually testing Roberta, the workflow is similar to the workflow of BERT previously discussed. However, we are removing that next sentence prediction pre-training task and only having that bidirectional context understanding.
Now we're going to talk a bit more about ExoNet. This is the flowchart for ExoNet. As I said in previous videos, ExoNet is permutation-based, it's bidirectional, and also uses masking for guessing the words. It's really good at guessing in the context, because it doesn't just guess the next word or the previous word. You can mask any word in the sentence. It's going to guess based on the context. That's why it's really good, but it's also why it takes a lot of computational resources.
Now, we mentioned before that BIPOL is a two-stage system. Now, let's take a quick look at kind of what that looks like diagrammed out for if you were to actually work with it. Now, you start off the same way you would any language model. So you start off, you take your input, you clean it up a bit, and then you tokenize it. You break down your sentences into little lexical units that the language model is capable of understanding. And now, there's two analyses that happen, or up to two analyses. So first what happens, your data gets passed off to the existing model. And this is actually where all of the machine learning would happen, because we're kind of built off of this other probably neural network language model for our corpus analysis. So that model is trained based on a data set like BABE, and then we take its conclusions back. And then we take kind of the tokens we have from the sentence, which are hopefully roughly word level, and then we perform frequency analysis. We accept some kind of human-tuned lexica of sensitive terms, and we count how often they occur. And using those, we can produce our output predictions for, based on the corpus analysis, is this text bias? And if it is, how so? Does it focus on particular kind of wording? For an extreme example, does it use slurs? Things like that, and BIPOL basically annotates these predictions with these data from the lexica. Now, let's talk a little bit about how these models can be combined. Now, it's a fairly common situation to have a few different models with slightly different approaches to classifying data, and actually that's quite a good thing. If each of a few models has some different features it focuses on in the data, which you could think of as a kind of specialty, then maybe by combining models, we can get the best of all worlds and get insight from more of the features at once. In some sense, the more variety, the better. As a side note, this is why we've actually decided not to include BIPOL in our combined model. Its binary bias opinion was based entirely off of its component model, and the places where it added information didn't really add any power in the places that we're trying to add power, so it really didn't bring any variety to the table. The idea of bringing multiple models together to build a stronger one is the basis for kind of a whole family of methods called fusion methods. Sometimes, when it comes to fusion methods, the simplest solution is the best. You can just take a vote, just ask each model their opinion and tally them up. There's ways to improve on that too, like you could give different models different voting powers to kind of refine your process. And of course, you can always make things more complicated. There's a fantastic review by Mohammed and Cora that discusses a ton of different fusion techniques and a whole family that they call ensemble methods. They broadly categorize certain ensemble methods into bagging, boosting, and stacking. In bagging, you split your training data up and you actually train your component models on different sections of the data to really accentuate and bring out their differences before you take your vote. And the idea here is really to focus on variety. The hope is that the vote has a more diverse range of opinions and backgrounds to draw on. But, of course, there's plenty of other ways too. In boosting methods, you modify the component models slightly and build a sequential ensemble like we have on the left. The idea is that each component classifier knows the opinion of the previous classifier as an input, and then it can use that to inform its own rating. Another kind of system called stacking uses what's called a parallel ensemble. And here, the component models operate independently, and they can even operate at the same time. Then, at the end, some new system decides the overall classification using the opinions of the component models as inputs. This is really an extension of the voting idea we talked about earlier. In fact, the ensemble in this case could be as simple as taking a vote, or as complicated as a whole new neural network. There's really a lot you can do with this idea. Now, Jamie will talk about the system that we actually built.
Now we're going to talk about the project demonstration for validation in a project. This is the ensemble workflow. As we can see, it starts with the dataset. We got the BAPE dataset. Then we have the data processing, which is cleaning and balancing. We took out the no agreement because it lowered the scores for all models and made them worse. So we just have bias and non-bias. Then we trained those models based on the data we processed. We fine-tuned them. We assembled them using a voting system, which only 3 of the 4 models trained are in the ensemble, because T5 had a lower score than the others, and the algorithm decided to leave it out. I'll explain more about that later. Then we tested and validated scores, F1 scores, the accuracy, precision, recall, and finally we have the live testing, which I can show you now. This is an example of our model. You put the sentence in, and based on our dataset, it learned, and it's gonna say if it's biased or non-biased. Our dataset, it's expert reviewed, so most of the times it's correct. I think we did a pretty good job in the ensemble. It gets most of the sentences right. Some of them it cannot get it right because the sentence is too complex or there's something messing with the model. But most of the times it gets it correct. Now we're going to talk about the experimental results and discussions.
To evaluate our models, we used a couple different metrics. The first one, precision, is a comparison of the true positives to the total number of model-predicted positives. Recall, similarly, is the number of true positives compared to the number of actual positives. F1 is a combination of both of these scores. Another one not pictured here, accuracy, is simply the number of correctly predicted results compared to the total number of results.
For the metrics, we can see the scores for ExoNet, Roberta, BERT, and T5 at the top. As we can see, ExoNet, Roberta, and BERT have similar scores, while T5 has a much lower scores. At first, we couldn't train T5. It was really complex. It wasn't working. We managed it to work, but still the scores weren't great. Then we can see in the orange box the ensemble weights. These are the weights for the voting in ensemble. We used an algorithm that chooses what's the best F1 score with all the possible combinations of weights. And in the best combination, it left T5 out, and Roberta controls 60% of the votes, which was, we kind of expected this. And at the end, we got pretty good results. F1 score of 0.9125. That's a really high score for a bias detection model, and it's better than any of the individual models that we trained. Here is the graph for the results. As we can see, the blue bar is our ensemble model. It's better than any of the models and much better than T5, for example. Even a little difference makes a big difference when a little difference in the graph makes a big difference when detecting bias or non-bias in sentences. It's a complex topic, and I think we did a pretty good job.
As we've been working on this project, we have learned an absolute ton. We've learned how to use all sorts of new tools. We've learned how to work with data using NumPy and Pandas. We've learned how to work with transformers, how to express models in PyTorch, the tools available to us through scikit-learn. We've learned what ensemble models are and combined models. We've learned how to use fusion methods to get models working in tandem. We've learned how to evaluate different AI systems. We've learned what an F1 score is and how to calculate it. We've learned so much about kind of working with models in general. We've learned about kind of the mechanisms for training and the trade-offs that we face in practice. We've discussed in class, stochastic gradient descent versus kind of batch learning and things like that. And it's been really, really cool to get to see those in practice and to get to kind of get used to them and get a feel for kind of what these trade-offs actually mean, what training time can actually be, and kind of the incredible performance you can get out of these models if you know how to do it. So truly, this has been a wonderful experience. We have learned an absolute ton. And we've kind of learned a lot about the problem too. We have a lot of conclusions and some ideas for future work, and I'm going to let Amanda take it from here.
Next, we'll discuss conclusions and future work. So with media bias being a difficult area due to its subjectivity, we did have some challenges with getting our model to be super accurate. So when doing some testing, we uncovered that there are some areas of improvement needed. So with the model not being 100% accurate due to these challenges, we found it would be useful to expand on our model by pre-training on different data sets, so potentially looking into using the MBib dataset, which contains a lot more data and could help make our model more accurate. But overall, we learned that this area is definitely a difficult task to use AI for, just due to bias itself being difficult for a human to even identify. So we are hoping to expand on this by including more data.